Hi, everyone. All right. Hi, everyone. Welcome to the next session. Short announcement about internet first. Someone was asking. If you have any questions about the Wi-Fi, go out to the front desk and talk to Hannah. She'll let you know. And we're going to get started with Bill Jorgensen talking about free energy calculations from butane to COVID-19.
Okay, well, thank you very much. Thank the organizers. Thank Novartis for the lovely facilities. Sophisticated audience, it's really nice. You all know about free energy, so I'll just get right into it. I'll give you a little of the history, but what we've been doing for the last 20-some years is using FEP calculations to drive lead optimization. And the basic approach that we use for drug discovery is to start with a crystal structure, and then we do virtual screening, docking, and we also use my de novo design program BOMB. This delivers micromolar hits, and then the fun begins to do the lead optimization, where we do a lot of structure building, again with my BOMB program, and then FEP calculations to decide what molecules to make an assay. And so we go through several cycles of this as we make the compounds more potent and to get to low nanomolar levels. We also worry about properties very much. So in the early 2000s, I wrote the program QuickProp, which was an AI ML program, though I didn't bother to call it that at the time. But it's still widely used and distributed kindly by Schrodinger. So there are other issues here that we've already heard about: force fields, convergence, etc. So here's a little of the history. Gibbs, of course, was a professor at Yale in the late 1800s. His father also was a classics professor at Yale. You can visit their graves if you'll come see us at Yale. And also right next to them are Kirkwood and Onsager. So it's interesting, the Grove Street Cemetery for statistical mechanics history. So, maybe I can end up there. I don't know if there's, I'm not sure there's any space left. So might have to do some special sampling. Thermodynamic integration, again, Kirkwood, you're familiar with that, and that's 1935. Kirkwood was a professor at several places, Caltech, Chicago, and he ended up at Yale. So this was actually pre-Yale work, but he was, of course, continued to be very active at Yale and Stat Mech. Statistical perturbation theory is what we called FEP before the name got changed. And you can read about statistical perturbation theory from the physicist Peierls. And this is written up in Landau and Lifshitz, 1951. And you'll see what I call the Peierls equation, which is, in fact, first order expansion of the Zwanzig equation. Zwanzig was also at Yale when he did this work and was a postdoc of Kirkwood's, but he published this paper on his own. I suspect that earlier people knew of this equation, but it appears it wasn't written down until Zwanzig. Then you may or may not know that umbrella sampling came along much later. In fact, that happened in 1975. Torrey and Below at the University of Toronto. And around that time was early work on doing liquid simulations of other than the simplest systems because of computer resources. And the people that were active, I think the most active at that time were Bruce Byrne and myself doing early applications of umbrella sampling. So this was the type of thing that would have been a big deal in 1980. It would have been butane and Leonard Jonesium, but now we could do butane. Both Byrne and I published on this in 1982, butane and water versus butane pure liquid or the gas phase, where there was a controversy at that time whether you would see a hydrophobic effect on butane conformation, and there were earlier theories. WCA theory said no, but here from the simulations, you see that there is a shift to give greater gauche population. So my history of free energy calculations goes back to around 1980, where we were doing direct sampling on pure liquids, getting torsional energy profiles, and then that's why we got interested in the umbrella sampling, because you couldn't get over even little barriers without doing something special. So then 1983 was when tip 3P, tip 4P water were introduced 40 years ago now. That was a big deal because water was thought to be complicated. You need complicated functional form. But in talking with others, there was a pressing need to explore this. And by that time, I had written NPT Monte Carlo code, so I could compute pressure, I could compute density and heat of vaporization. And this was the first force fields, along with SPC, which is basically similar to tip 3P, that was developed where one could do repetitive simulations to optimize the parameters. And then also the functional form was now compatible with the protein force fields that were being developed at that time, the Lifson style protein force field. So that then enabled doing simulations of proteins in water. And that didn't occur until about 1985. There weren't any notable simulations of proteins in explicit water. And then it was even in 88, I went to a meeting in Sweden where that was the new thing. Was a few groups, Levitt, my group, people in Lund, were doing simulations of proteins in water. And so then where did FEP come in? Well, we were obviously interested in free energy methods. You can read about SPT, statistical perturbation theory, in the Macquarie book. I was aware of that. And so I had also had a chat with Andy McCammon, who was interested in this. And at that point, I said, okay, I'll give this FEP, SPT, a try. And that meant, there was no code. You had to write your own code. So the code that I added to my program, which ultimately became the BOSS program. And we'll talk about that a little bit more. And that led to this very exploratory work on the ethane to methanol calculation in 1985, which is the first, I would say, modern FEP calculation. It includes windowing. I introduced single topology FEP there, also double wide sampling. It's all in that paper. Then the period of that calculation took 6 weeks on our only computer. Okay, the University of Purdue at the time had had a total of 2 or 3 CPUs. We had one CPU in our lab and it tied it up for 6 weeks to do that calculation. So that's why things got off to a slow start. And then, so we and others then jumped on this. Peter Coleman, very excited about this work. I had various exchanges with him about that. There's a lot of interest in studying just intermolecular interactions, potentials of mean force, and then slowly working on host-guest systems, typical organic host-guest systems. Then eventually, people started doing proteins and water with FEP-type methods. Our own group, we were doing that by 97. Then here, protein ligand binding, published some papers on that. Also, the other thing to note is our calculation 84, the SN2 reactions in solution. This is the first calculation where one could compute the solvent effects on an organic reaction in solution. That was done by umbrella sampling. So FEP wasn't on board at that point. But once FEP did arrive, it had real advantages over umbrella sampling in that you could control the reaction coordinate, if you will, and progress rather than having to cook up biasing functions as you do with umbrella sampling. So then what happened, I've been excited about FEP since that time. Around 2004, I committed to trying to do prospective lead optimization with FEP. I believed it would work, but unfortunately there had been very few successes. Prior to that, everything was, I'd say, very just an episode here or there where somebody reported an FEP calculation. But we needed to do it in a systematic fashion. That required me to establish our experimental group because you can't get people to do synthesis for you very easily. So that started in 2004. We started getting very good results of working on HIV target at that time because of people at Yale were very interested in that. Tom Steit's group had determined the crystal structure of HIV reverse transcriptase. So that was the system we were working on. And I have been involved with Schrodinger since its beginning, and I kept them informed of what we were doing and showed them that we were making good progress on predicting, actual predictions of changes in free energy of binding. So Schrodinger, first foray into FEP calculations, they took my Monte Carlo program, MC Pro, and called it MC Pro Plus. As you might imagine, QuickProp didn't become QuickProp Plus, but that was the early days. I'm sure it would be QuickProp Plus today. But so that was Schrodinger's introduction to FEP. They put a front end on it and worked with it. They, I think, had good results, had customer interest, and then eventually they saw the future, and I think the community is very grateful to their efforts. And FEP Plus then, with Desmond and doing MD, was introduced about 10 years later. So going on, just there's the Zwanzig equation. The Zwanzig paper, the FEP calculation there is a rigid sphere to a Leonard-Jones gas. Okay, so a little esoteric. And then, like I said, I think the first modern FEP calculation is the 1985 ethane to methanol one. That, of course, opens up general free energies of transfer. Protein ligand binding is just a free energy of transfer. Changing a ligand from to another in water versus bound to a protein. It's a free energy of transfer. Also then QMMM very much benefited from FEP because you can just drive reaction coordinates and compute the free energy changes. So you're familiar, now we'll turn to focus on protein ligand binding. This is the setup we use, protein ligand, a couple thousand water molecules in a ball, the usual thermodynamic cycle. You convert green ligand to blue ligand in water. That's just the ethane to methanol calculation. And then the same thing, the other part of the cycle is when it's bound to the protein. So this is wonderful in that you can predict the effects of small changes on free energies of binding. So what happened, though, is we recognized this as a community in the 80s that this would be possible, but nothing much happened. Like I said, as of 2004, there was hardly anything in the literature, and we really were committed to it. So we worked hard on the HIV system. We had enough positive results we could publish this Counts article in 2009. And in that article, we pointed out that we'd had great success pursuing things systematically by FEP, and this is what we still do. We do small substituent scans. These data I'm showing you here, this is experimental data on compounds that we synthesized and were assayed by my collaborator Karen Anderson. This is a typical HIV cell assay. And starting here with a de novo compound, it's 30 micromolar. If you make small changes, you just happen to put a methyl group there, you happen to put a chlorine there, and next thing you know, you can be at 40 nanomolar. So we achieve this by, whenever I see a benzene ring, we do scans. We do chlorine and methyl scans. I pick those two because they're of opposite polarity and they're similar size. Also, of course, heterocycle scans. And so we've done things like this, the pyrazine greater than 15 micromole, pyridine, pyrimidine 200 nanomolar. And then in a paper in 2006, we got a little fancy going through different bicyclic heterocycles, and this all of a sudden we're at 6 nanomolar. Same linkers. So again, substituents, heterocycles, and linkers. That's what you want to be working on. That's what we pointed out in that paper, and we've had a lot of success with that. We published many papers on discovery of non-nucleoside RT inhibitors, starting with this one here, 2 nanomolar compound in 2006. This paper, I always tell people to write that reference down because it hasn't been cited enough. You got to figure out how to. It's a really good paper, Jack's communication on doing heterocycle optimization. It worked out really well. And then here we are a few years later, we're 2.5 nanomolar. And you might be wondering, well, you haven't made a whole lot of progress. Problem with HIV, like COVID, is it mutates. So the early compounds were effective against wild-type HIV, but we had to do a lot to make the compounds have broader spectrum. This compound is very good against Y181C as well as a wild-type. Other stories here, this was a fun story where we took a dead docking compound. The pose looked promising. We stripped off the substituents, followed our procedure, rebuilt, changed heterocycles, and before you know it, we're at 1 nanomolar. This one I'll just highlight, our favorite series of compounds. This was a docking hit, 5 micromolar docking hit that we evolved into actually a 55 picomolar compound, certainly the most potent anti-HIV compound known at the time, all with FEP guidance. Then we've also wanted to get rid of the cyanovinyl group, which you do see in some HIV compounds, and that we chose by looping it into a bicyclic heterocycle, did the optimization of the heterocycle via FEP, and it brought us to a ring system I wasn't that familiar with, but we included it in our FEP calculations in dolazine. And that compound is, for example, 400 picomolar in wild type and 10 nanomolar against a very difficult double mutant that's observed clinically. So that brings us to COVID. So 2020 rolls along. We're obviously been working on antivirals, so we have the setup for that. So COVID comes along. And January, February, next thing you know, March, we're shut out of the lab. Okay, things shut down, but we could still work on computer things. And so I asked the people in the group to do docking on the main protease. I won't go through the life cycle of the virus, but if you knock out the main protease, the virus doesn't replicate and you're in good shape. So what I asked them to do is to take a library. I keep of 2,000 oral drugs and to dock them. Of course, we're doing consensus docking here. We use Glide, Autodoc, Vena, Autodoc and a second variant of Vena. So we do consensus docking on the 2,000 compounds. What I was hoping for is just to see some drugs that would give us a reasonable starting point. I wasn't expecting to repurpose, okay? But I wanted just a reasonable starting point. And the fact that I'm starting with a drug is a good thing. You know, it has drug-like properties. So I called up Karen and said, Karen, let's work on this. Can you get the plasmid? And also there's an assay that's in the literature, this FRET assay for peptide cleavage. And we did the docking. We, of course, visualized the top structures. I personally sit there, visualize probably 200 of the top consensus compounds, and I picked 17. We purchased them, gave them to Karen's lab, the assay, and turned out 14 of them showed some activity in inhibiting SARS-CoV-2 main protease. And the most potent ones were in the single digit micromolar range. So benidipine, boceprevir was a known SARS-CoV-1 inhibitor, but the others were not known. And so we had these compounds, we had the docking poses, and now the thing was to pick one that we're going to try to lead optimize. Now, if I was here at Novartis, maybe I could have picked 5. But, you know, in my world, I have 2 synthetic chemists on this project. We picked one compound. I didn't mention what it's going to be, and it's probably a surprise some people, particularly one of the reviewers who basically dismissed all of the compounds above 100 micromolar as useless. But we picked this parampenyl, 100, 250 micromolar, weak inhibitor. But why I picked parampenyl was I liked the pose. Sometimes I don't like the poses. I see clashes, I see confirmations, but I like this pose. And I also am looking at it and I say, I know how to make that molecule. Okay, so this is a core with 3 aryl groups on it. So this is Suzuki type coupling, Chan-Lam to make the one linkage over here. And so I thought the pose, this is the glide pose, looked good. And I could see likely ways of improving this. So I see the nitrogen here, the pyridine isn't doing anything, so I don't need that. The carbonyl here, if you look at this picture, isn't doing too much, but there's a lonely NH on the other side. Maybe I could flip the carbonyl over there. There's a histidine down here that would like to hydrogen bond to somebody, but it just has that phenyl, so that's a flaw. I also could see maybe some space over here, but I don't know quite how big it is. And then this ring, cyanophenyl is okay. I mean, it's obviously an approved drug, but not my favorite substructure. So maybe I could do something, change that ring system, pick up some hydrogen bonds with this region over here. So I'm spending a lot of time looking at structures, if you can understand. So then what I do is set up the FEP calculations to check these features. So this is from my actual, very high tech here, my Excel spreadsheet, where I set these up, ran them myself with my MC Pro program because I'm familiar with it. And what did I do? Well, I did a scan of this left ring that was a phenyl, and to check all the nitrogen heterocycle possibilities. So I'm going 2-pyridyl, 3-pyridyl, 4-pyridyl, some pyrimidines, etc. And what lit up was the 3-pyridyl. So this is the difference between the bound and the unbound, minus 3.5. So that's looking good. And then I did that flip of the carbonyl, and that was very good. That was minus 4.7. And I also did a scan then of the right benzene ring, did a chlorine scan, and that said putting a meta chlorine in would fit that pocket. So then I asked the 2 synthetic chemists to make these compounds. I've also done additional modeling with bomb that indicated to me maybe I could put a uracil here and pick up some hydrogen bonds with this edge on the bottom edge there. So the first three compounds they synthesized are shown here. Here's parenteral. I'm orienting everything in the same way to show you what we did. And so parenteral we think is 100, 250 micromolar. There's interference with the assay. The first three compounds we made were 10, 6, and 4 micromolar. So this shows you can very quickly. How much? Oh, wow, well, we're in trouble. Okay, well, that's too bad. So, okay, so that compound, so now we're at low micromolar. Here a month or so later, we got the X-ray structure. It was exactly as we predicted. Then the next thing I do, starting with that, is I recognize that this chlorine could be replaced, grow up in a channel there. And we do a simple scan, methylethylpropyl, OR groups, etc. This lit up O-propyl, make that compound, we're 140 nanomolar. The uracil is 120 nanomolar. And then I also, from modeling, could see I could put a benzyl group in this region, another crystal structure. And we did, as soon as I have that benzene ring, I'm going to do a scan, chlorine and methyl scan. Says chlorine ortho or methyl ortho should be dynamite. We make those compounds and we got 18 nanomolar. At this point, I don't think we'd made fewer than 30 compounds. This we published in ACS Central Science in early 2021. We have many compounds that we published in this paper that are below 50 nanomolar. This has to be tested in cell assays, and so we're going to the med school again, the BL3 facility. It's airborne, so you have to have full hazmat. And we do the cell assays, and some of the compounds aren't that active because they're not that permeable, but we have a compound like number 19 here that's 50 nanomolar, or 80 nanomolar in our assay, and Johnson & Johnson assay, it was 50 nanomolar in their assay. And you can compare this with nirmatrelvir, the Pfizer compound. First of all, I sure much prefer synthesizing our compound. And you don't need ritonavir with our compound. Our compound's also 10 times more potent in the cell assay than nirmatrelvir. So, and it's great in mice. Here's oral mice, vehicle mice, and you see very nice protection with our compound. This is the key thing, is the power of FEP, the timeline. So we had basically parenteral on June 15th. On August 7th, we're at 4 micromolar. September 2nd, we're 140 nanomolar. And October 22nd, we're at 18 nanomolar. Again, just 2 synthetic chemists and maybe synthesize 30 compounds. So this is very rapid response. I will say just one thing here. We have run some unpublished stuff checking how to do absolute free energies of binding. I mean, that's been a theme. And we introduced also the first double annihilation calculation. It was methane dimer calculation in JChem Phys, probably 1988. And what we have now is this wonderful data set. We have here's 16 of our MPRO inhibitors. We've got 12 crystal structures. So we basically have crystal structures of all of them. And we've run FEP double annihilation, metadynamics, and docking. First of all, the double annihilation, we're running this with you can read our force fields, and then this is being run with GROMACS 2019, so 6 degree of freedom restraints. And this is long sampling, and this is what we get for this range of compounds covering 10 to the 4th in activity. So R squared of 0.6. The problem is you have these cases like here where you have the same experimental activity, but you still have a range of like 3 kcals per mole in the predicted activity. So this isn't ready yet, at least in our hands for lead optimization. And I'll just very briefly, I can tell you, we've done, and this was with 3 replicas on each one of those. And metadynamics and docking, well, of course, as you might expect, there's no free lunch. So metadynamics, this is, we're using now NAMD on this. We've tried very hard. Ideal data set, and we'll publish the data set for you. It's already published in pieces, but we'll put it together for you. And again, it's just not good enough. So you have an R squared of 0.2. And the docking here, this, and we've run, this is 5 replicas, we've run 15 replicas. That's what we'll be publishing. And the metadata is just too noisy. So just each trajectory gives you very different free energy profile. So I'll stop there, and I hope to provide some education. It's utterly frightening for me to stand here and recognize that I was doing FEP, free energy calculations before most of you were born. So this field's been around for a while, but it was a very slow start, as you know, many things. Again, I credit Bruce Burns' group for hanging in there and doing some of the early work. All custom software. Burns programs have never been, appeared. You know, my BOSS program is freely available. People download it all the time. It was very, rough in those early days, and it wasn't sure where things were going. When we published that FEP, the ethane to methanol calculation, I would give talks on it. And I remember there were 2 very distinguished people who were just sitting there shaking their head because it was so impractical, okay? Here, this guy has taken 6 weeks on his only computer, and all he's done is convert ethane to methanol and get a difference in free energy of hydration. So seriously, it was very exploratory at that point. But then, we've all hung in there, and it's just so, refreshing to me, really emotional to see this type of audience and interest in these esoteric things that we were playing around with in 1980. So thank you very much.
We have time for one quick question for Bill. Okay, then I'll ask. Bill, what do you think is the value of human intuition versus the computer? And for example, you chose 14 compounds for Emperor. How important was you looking at them?
Well, I would change it to human experience, maybe. Intuition sounds a little bit irrational. So no, it definitely, I advocate very highly, just really spend a lot of time looking at crystal structures and then compare those with your docking structures. So yeah, it was important to screen. Brian Scheuket talks about this all the time too. And he and I are completely simpatico on this idea. You really do have to, when you're looking at the docking structures, you got to cherry pick them. Or again, if you're a big company, maybe you can just buy the top 200 hits. I mean, so we've only bought 17 compounds. So if we had bought the top 100 from the consensus docking, if you bought all 100 of them, you would have come across those 17. So it's a little bit of a question of resources, but good point.
Thank you very much.
And thanks again. Here comes John.